So we defined a group and talked about groups of symmetries of different mathematical objects like geometric shapes or equations or surfaces or whatever. We want to be more specific this time and write down some examples more systematically in a way in which you can actually calculate with these groups. Let me make some space. Oops. So, giving examples of groups. And the definition is still on the left. So the first set of examples, and some of these won't look like symmetries of things, but you can actually make them look like so, but right off the bat they probably won't. But the definition is right here. All I have to give you is a set G with an operation, binary operation, called to be called the group law, and a special element called identity, such that these three axioms, associativity, identity, and inverse axiom, are satisfied. The first sort of examples, the ones that you meet first, come from different number systems. Examples from number systems. Maybe we'll categorize them like so. The first one is the set is Z, the operation star is plus, and the identity is 0. So what does the three axioms say in this case? It says that the first axiom reads A plus B plus C is A plus B plus C for all A, B, C in Z. That's true, right? So we have verified the first axiom. What does the second axiom say? It says that A plus 0, the identity, remember, is 0, is A, which is same as 0 plus A for all A in Z. True again. What does the third axiom say? That for all A, there exists a guy. Now here's the problem. The thing in general is called A inverse, but here I want a guy in Z such that when you compose them, meaning in this case the composition is plus, you should get 0. What is that thing? There is such an integer, but it does not called A inverse, it's called minus A. So to get used to this thing, that what is in general called A inverse, when the group operation is written sort of multiplicatively, sometimes is known by other names. In this case, it's known by minus A. So in this group, it's called an additive group of integers. Group of integers. The inverse is called negative of A, actually, the inverse of A. At any rate, the three axioms are true, so this is a group. So once you have that one, very similarly you could take the rational number system or the real number system or the complex number system or your Z mod PZs, let's say, things that you have seen, congruence mod n, if you have seen them. And these all have a plus in them and a 0 in them, and they form a group. In fact, if you take f star to be f minus 0, meaning the non-zero rational numbers or the non-zero real numbers, then there is a different group structure on them. On the non-zero real numbers, let's say, you could take the multiplication operation, and instead of 0, you can take 1. This also forms a group. And in this one, the first axiom just reads A times B times C is A times B times C. The second axiom just reads A times 1 is A is 1 times A. And the third axiom just reads for all A in F star, same. And the third axiom reads that for all non-zero real number there exists a real number, again non-zero, such that when you multiply them with this guy, and now in this example multiplication really means multiplication of numbers, you get 1. And in this example, indeed, this guy is called A inverse, sometimes called 1 over A, the reciprocal, sometimes also called A inverse. So these are sort of straightforward examples, and these are all actually examples of abelian groups. Because in all these examples, the order of multiplication does not matter. In fact, if you know what a ring is, if you take the additive group of a ring, you always get a abelian group. And if you take the units of a ring, you always get a multiplicative group. So my next example would be, this is sort of a super important example. Let's look at automorphisms of a set, or permutations of a set. So let S be a set, and let perm of S, that's going to be my notation, is the set of all bijections from S to S. So an element of perm S is a function from S to S, which is a bijection. Bijection, remember, means 1 to 1 and on to. A function is 1 to 1 if different elements in the domain go to different elements in the range. And a function is on to if all the elements on the codomain is hit by some element of the domain. So given any element in the codomain, there is an element in the domain such that when you apply the function, you hit that. Okay? If you haven't thought about these things in a while, please revise this notion of 1 to 1, on to, and bijection. So I want to look at the set of all bijections from S to S. And in this is my G. And the group operation is composition of functions. And the identity is just the identity function of S, meaning E of an element is that element for all S in S. So let's maybe do a little example. Let's say S is the set 1, 2, 3. Then what are the bijections from this set to itself? So here is one bijection, F1. Here is another bijection. F1 of 1 is 2, F1 of 2 Sorry, let's not call it F1. Let's call this F2. Takes 1 to 2, takes 2 to 1, takes 3 to 3, etc. Writing all this becomes too much work. One uses a shorthand notation. One says F1 is this thing. So you write the 3 elements on top and then write where they go at the bottom. So, sorry, this is F2. F2 will be denoted like this. The 3 elements, where do they go? 1 goes to 2. 2 goes to 1. 3 goes to 3. Let's do another one. F3. Maybe 1 goes to 1. 2 goes to 3. 3 goes to 2. What would be the notation for this one? 1 goes to 1. 2 goes to 3. 3 goes to 2. And then there are a few more you can figure out. There's this one that flips 1 and 3, keeps 2 itself. Then there is one, there are 2 that sort of rotate things circularly. This one takes 1 to 2, 2 to 3, 3 to 1. And there is one that takes 1 to 2, 1 to 3, 2 to 1, and 3 to 2. 3 goes to 2, 2 goes to 1, 1 goes to 3. You can check that permutations of this set 1, 2, 3 is these 6 elements. This one is, of course, the identity. These are the 6 bijections. This set has a name. It's called S3. It's called the symmetric group, or the permutation group of n letters. 1, 2, 3, n. Sorry, this one is the symmetric group of 3 letters. 1, 2, 3. Similarly, define Sn, the permutations of n letters. And this is extremely, extremely important group. Let's just work out one multiplication in this group. What happens when you apply, let's say, at random, F3 and then F5? What is F5 times F3? Let's learn to multiply them. So that's same as, what is F3? That one. And what is F5? So what do I have to do? I have to take 1, 2, or 3 and track them. First apply F3 and then apply F5. It's better to maybe track them this way. First apply F3. And what happens when you apply F3? 1 goes to 1, 2 goes to 3, 3 goes to 2. And then you apply F5. When you apply F5, 1 goes to 2. 3 goes to 1, right here. Right here. So 3 would go to 1. And then 2 would go to 3. So what's the result? The result is 1, 2, 3 going to 1 goes to 2, 2 goes to 1, and 3 goes to 3. So that's the one that flips 1 and 2. That one is called F2. Yeah? So this is how you multiply permutations. Remember, this is first F3, then F5. You just work out what it does to 1, 2, and 3, and then you know which function it is. We'll work with this more.